Hello everyone, I hope you're all doing well. We will be solving a problem on Cartesian 2D vectors today, okay? Alright, so here is the problem. I'm given the x and the y coordinate frame first. So here is the vertical y direction, and then here is the horizontal x direction. So this is the x-axis, the y-axis. I'm going to mark the positive and negative unit vector directions. This is positive I, and then this is positive j, and this is going to be negative I, and this is going to be negative j. Okay, now on this coordinate frame I'm given the following force vectors. So here is a force vector which I'm going to call as F1. F1 has a magnitude of 800 newtons and makes an angle of 60 degrees with respect to the x-axis. Then I have the force vector F2, which is drawn in the following manner. F2 has a magnitude of 600 newtons and makes an angle of 45 degrees with the vertical y-axis. And lastly, I have this force F3, which is sitting in the fourth quadrant. F3 has a magnitude of 650 newtons, and I'm given a small triangle to accompany this particular force, and I'm going to draw that triangle right here. Okay, this triangle is called as the slope triangle, and it has sides 5, 12 and 13, and as you can obviously see, this is a right angle triangle. Okay, so this is called as a slope triangle. All right, so what are the things we need to do in this particular problem? First thing is to obtain the magnitude of the resultant of the vectors F1, F2, F3. Okay, that's the first thing we need to do. Second thing we need to do is express the resultant vector in its Cartesian form. So express the resultant vector in the Cartesian form. And the third thing is we need to find the angle made by the resultant vector with the positive x direction. Okay, so find the angle made, the angle between the resultant vector and the positive x axis. Okay, these are the three things that we need to do in this particular problem, and we are given three different forces: force F1, force F2 here, and then force F3. And one quick bit of information is that if I look at the angle of 45 degrees, I would also be able to calculate this angle here as 90 minus 45, which is also equal to 45 degrees. Okay, and this is typically my preference to write the angles with respect to the x-axis. All right, so with these things that we need to find, what is the key idea in this problem is the following. The resultant vector Fr is going to be given as the vector sum of the individual vectors. Okay, so this is a vector sum, and I want to underline that this is different from a scalar sum. So you see that I'm not just taking the magnitude of all these forces F1, F2 and F3 and adding them up. Okay, I cannot do that. I have to take the force vectors, write them in their component form, along the x and the y directions, and then do certain other things. Okay, so the basic idea is that I break the forces down, break each force into components along the x and the y directions, and then add the components in the same directions algebraically. Okay, and I can also make use of the fact that since this is a Cartesian system, the projection and the components are the same. Okay, so also make use of the fact that since system is a Cartesian system, in the Cartesian system, the projection is the same as the component. Alright, so these are the key steps in my problem. So break each force into their respective components, okay, along the x and the y direction. Then what we do next is we add the components up in the same directions, okay, and then this is not just done willy-nilly, you have to do it algebraically. Okay, that's an important thing there. And then we also make use of the fact that in the Cartesian system, the components and the projections are the same. Alright, and the key idea used is the resultant force is the vector sum of the individual forces. Alright, now I'm going to take each of these forces, F1, F2 and F3, and then I'm going to break them into their respective components. Okay, let's do that. So I'm going to take the force F1. Okay, and I'm going to draw the Cartesian coordinate frame here. So this is the positive y direction, this is the positive x direction, so this is x-axis, this is the y-axis. Then I have the force F1, which is sitting right down here. Okay, so this is the force F1. How do I find components or projections in the Cartesian coordinate frame since they're the same? From the head of F1, I just drop a perpendicular to the y-axis and the x-axis, okay? Or I draw a line parallel to the y-axis from the head of F1. Then I draw a line parallel to the x-axis from the head of F1. That line has to be parallel, okay? And then I say that, okay, wherever they intersect the x and the y-axis is the respective components. So starting from here, all the way to where this line intersects is the component F1x, the component of F1 along the x direction. Likewise, I go from here all the way to where this force is intersecting. That's going to be the component F1y, which is the component of F1 along the y direction. And since it's a rectangle, I can pretty easily say that, okay, this guy here is also going to be F1y. Okay, and I know that the inner angle is given to me as 30 degrees, okay, 60 degrees, I'm sorry. So I'm going to be writing this angle here as 60 degrees. First thing I realize is that F1x is along the positive x-axis. Okay, so F1x is along the positive x-axis. Likewise, F1y is along the positive y-axis. Okay, this is the information that I see from the problem. This is a right angle triangle here. Okay, and I can say that, okay, F1x is F1 cosine 60, F1y is F1 sine 60. Okay, so this is going to be F1 cosine 60, and this is going to be F1 sine 60. And so if I now write the force F1, I have the following. Okay, so force F1 is its component along the x direction and its component along the y direction, okay, which in our case is going to be a positive f1x in the I and a positive f1y in the j, as you can see, okay, which means that the force F1 can be written as F1 cosine 60I. Any force is its magnitude times its unit vector plus F1 sine 60 times j. And this is going to be so many newtons. Okay, and I'm going to underline this particular answer. Typically what you'll see is that I will not be substituting for the numbers right away. I will rather keep them in symbolic form and then do the substitutions later. Okay, so this is the force F1. Now I'm going to look at the force F2. Okay, so take a look at the force F2 and we give it the same treatment. And we say, okay, I have the Cartesian coordinate frame, which I'm going to be drawing here. Where is the force F2 sitting? The force F2 is sitting on the second quadrant here. Okay. So if that is the case, so here is the force F2. And we found out that the angle made by this force with the x or the y axis was equal, and that was 45 degrees. Okay, so those angles were given to us. All right, now what am I going to do? And of course I don't need to write both the angles, so I can write either one or the other. So I'm not going to write the one with respect to the vertical. Okay, let's keep doing that. From the head of this force I drop perpendiculars onto the positive x and negative x and positive y direction. So first of all, here is my y-axis. I'm going to extend this a little bit. Okay, so here is the y-axis. Here is the x-axis, which means that the unit vector in this direction here is going to be minus I. Okay, and the unit vector, of course, along the positive y direction is going to be plus j. Okay, so if you want, we can squeeze that information right in here. Okay, so that's going to be plus j. Okay, and just for the sake of convenience, I'm going to move this guy and maybe bring that somewhere here, okay, so that we don't confuse the I with that. Okay, so here is the force F1, and as you can see, how do I find the components? From the head of F2, I drop a line parallel to the x-axis, I drop a line parallel to the y-axis. They will intersect at certain points, and I therefore get my components. Okay, so this is a right angle triangle here. This is also a right angle triangle right there. Starting from the tail of F1, F2, all the way to this point of intersection is the component F2x. Starting from this pinned point here all the way to where that point intersects, that's going to be the component F2y. And since it's a rectangle, I can call this as F2y as well. Okay, I know the components, I know the angle, I can use some basic trigonometry, but the first thing that I write down is the following. F2x is along the negative x-axis and F2y is along the positive y-axis. Okay, and then I start writing, okay, the force F2 itself is going to be its component F2x and component F2y. Okay, now we got to be careful. Okay, this is going to be F2x, the magnitude in the negative I direction, F2y in the positive j direction. Okay, and it's quite easy to see that the force F2y and F2x as F2 cosine 45 and F2 sine 45. Okay, so this is going to be F2 cosine 45, and this is going to be F2 sine 45, and take care of the directions, which means that the force F2 can be written as minus F2 cosine 45i and plus f2 sine 45j, and this is so many newtons, and we'll do the simplification towards the end of the problem. Okay, so this is the second force that has been obtained. Fantastic. Now I do the same thing for the third force. Okay, so I go to the force F3. We have a small slope triangle that is given to us, so let's see what the use of that is. Okay, so first of all, I set up my coordinate frame, x-axis, and then the y-axis. So this is the positive x-axis, positive y direction. I mark my unit vectors. Well, let me do the marking of the force first. So here is the force. This is the force F3. Okay, then I also mark the unit vectors, which I think is going to be useful for me. This is positive I, and look at this, it's going to be negative j. Okay, then I take the slope triangle. That information is given to me. I'm going to draw that here. Okay, so I have the slope triangle, and the sides of the slope triangle are given to me as 5, 12 and 13. Okay, then what do? From the head of F3, I drop a line parallel to the y-axis. I do same thing along the x-axis. I drop a line parallel to the x-axis, and then I say, okay, starting from the tail of force F3 all the way to this point of intersection, that's going to be the component in the x direction. Likewise, starting from the tail pointing in the negative y direction, as you can see, is going to be the component in the y direction. Okay, and which means that since this is a rectangle, I can say that, okay, this is also going to be f3x. Okay, so the first piece that I write down here is, okay, f3x is along the positive x axis, and f3y is along the negative y axis. Okay, then I see another thing. I see this little triangle here which I'm shading, and the bigger triangle, which is made up of f3, f3y and f3x. These are similar triangles. Okay, we are not going to prove that. So similar triangles, the triangles, the 5, 12, 13 triangle, and the triangle f3y, f3x and f3 are similar. Okay, it's fairly straightforward to see that. And since they are similar triangles, the ratio of the sides must be the same. Okay, and because of this, we can say that f3x divided by f3 is going to be the same as 12 by 13, and f3y by f3 is going to be the same as the ratio of the small side of that slope triangle to the hypotenuse. Okay, which evidently tells me that, okay, hey, f3x is going to be 12 by 13 times f3, and f3y is going to be 5 by 13 times f3. Okay, which means I'm now ready to write the force F3 in terms of its components. Okay, so the force F3 is going to be F3x, F3y. Okay, these are the vector ways of writing it. And if I make use of the directionality, F3x is along positive x, F3y is along negative y. And so this is going to be F3x in the positive y, F3y along the negative j. I'm going to substitute in terms of the ratios now, which means that F3 is going to be minus 12 by 13, F3i, plus 12 by 13 F3i, and the negative component is along the y direction, so that's going to be minus 5 by 13 F3j, and this is so many newtons, and we're going to underline this answer as well. Alright, so we have all the forces that are obtained. All we have to do is now vectorially add them up. Okay, so I have the force F3 here in terms of its x and y components. Then I have the force F2 in terms of its x and y components, and the force F1 in terms of its x and y components. Alright, so then I go to the last step of the problem. Okay, so then I say, okay, the resultant force is the vector sum of all these forces, okay, which tells me that, okay, Fr is going to be F1 cosine 60i sine 60j, then minus F2 cosine 45i F2 sine 45j, and I'm going to have 12 by 13 F3i minus 5 by 13 F3j. Okay, so this is the resultant force. And what do? I take all the I components, F1 cosine 60 minus F2 cosine 45, 12 by 13 F3, and add them up. And I do the same thing for the J components. This is called component-wise algebraic addition. Okay, so Fr is going to be F1 cosine 60 minus F2 cosine 45 plus 12 by 13 F3 in the I direction plus F1 sine 60 plus F2 sine 45 minus 5 by 13 F3 in the J direction. Okay, and if I substitute for F1, F2 and F3, substitute for F1 as 800 newtons, F2 as 600 newtons, and F3 as 650 newtons, and the answer that you'll end up with is the following. Okay, so Fr is going to be the following answer. It's 575.7i, okay, and then 867.1j, so many newtons. And what do you know? The way we have written the answer is called its Cartesian form. Okay, so this is called the Cartesian form of the resultant. Okay, so the Cartesian form, the 2D Cartesian form for any vector is you take the vector and write it in terms of its unit vectors. Okay, so this is the Cartesian form, and I'm going to underline that. Okay, so that's something that we found out. Now I can write this force in terms of its magnitude. So to find the magnitude of Fr, here is what I do. I say that Fr without the arrow is the square root of the sum of the squares. 575.7 square, 867.1 square to the power 1 by 2. Okay, which means that if I crunch the numbers, the magnitude of Fr is going to be approximately 1040.8 newtons. Okay, so this is the magnitude of Fr. This is something that we have found out. Okay, magnitude. And then we need to find the angle made by Fr with respect to the positive x-axis. and here is what I do. Okay, so I say that FR, which is 575.7I and 867.1J, I write it as some component in the x direction, some component in the y direction. Okay, and in this problem we see FRX, which is the x component of FR, is along, because there are no negative signs here, you can see that this is along the positive x axis. FRY, which is the y component of FR, this is along the positive y axis. Okay, and it can be quite easily seen that by comparison of the actual force and its component forms, we also see FRX is 575.7I, I'm sorry, not I, 575.7 newtons, and FRY is 867.1 newtons. Okay, so these are things that we see from the information that we have. I'm just going to make this a little better. Okay, all right. Right, so what do I do with this particular information? I guess that ended up being a disaster. All right, so what do I do with this? Here is what I do. I set up the x and y coordinate frame. Okay, here is the x-axis and y-axis. So positive x-axis, positive y-axis. I draw my unit vectors because they're positive I and j for the resultant. Then that's all I typically need. This became something other than the y. So this is the unit vector here is going to be the positive j unit vector, and I'm going to write this in the same color as the x-axis. Okay, so this is the y-axis, and then it's quite obvious to me that the x and the y components of FR are along the positive x and positive y. So here is what I do. Along the positive x direction, I draw the component FR x. Then starting from the tail here, I draw a component FR y. And how do I find the resultant force? Here is what I do. Okay, from the head of FRY, I draw a line parallel to the FRX force. From the head of FRX, I draw a line parallel to the FRY force. These lines are going to be drawn as dotted lines, right, if necessary. And then how do I find the resultant? The resultant is given by joining the pinned points onto the point of intersection. Okay, so this in reality is FR, which means that if I look at the y-axis, since it's a rectangle, I can call this guy as FRY as well. Okay, and likewise I can call the opposite side on the top as FRX. Now what do I need to do? I need to find the angle made by FR with the positive x-axis, which I'm going to call as theta r. And that's fairly straightforward. That is tan inverse of FRY by FRX. Okay, so tan theta r is FRY by FRX, which means that theta r is arc tangent or tan inverse of FRY by FRX. Okay, just want to make sure that this looks like an X. Okay, so this is FRX, and which means that if you solve for theta r, this is going to be tan inverse of 867.1 divided by 575.7, and this will ultimately give you an angle of 56.4 4 degrees. Okay, and what is this angle? This is the angle made by FR with the positive x axis. Okay, which is precisely what we were asked to find out in this particular problem. Okay, this is the angle made by FR with the positive x-axis. So the three things that we found out are theta r, which is the angle made by FR at the positive x-axis. The other thing that we found out was, okay, the magnitude of FR was this, and then we were also able to find the Cartesian form of the resultant force vector. All right, thank you very much, and please stay safe. Bye bye.